Some processes by which nuclei decay emit subatomic particles that have unique properties. So recall that protons and neutrons are made up of quarks with the nuclear strong force between them being mediated by gluons, which glue the proton together. So when these protons are in an unstable nucleus, so if you have too many protons versus neutrons, and vice versa, then a proton can transform into a neutron, and in the process of doing so, other particles are emitted. And now we'll go through some of the particles that are emitted in radioactive decay. So an alpha particle, or a helium nucleus, consists of 2 protons and 2 neutrons. So this can be symbolized as an alpha particle or a helium nucleus. Now other subatomic particles that can be emitted by nuclear decay are neutrinos, which are symbolized by a nu, and antineutrinos with a bar on top. So these have no electric charge and have a negligible mass. So note that every known particle has an antiparticle, and specifically electron-neutrinos are observed in the radioactive decay processes that we'll look at. Although there are other types of neutrinos, being a muon neutrino and a tau neutrino. So neutrinos and antineutrinos only interact with matter via the weak force and gravitational force, and this results in very little interaction with normal matter. And positrons, or anti-electrons, are subatomic particles that have an electric charge opposite to an electron, but have the same mass as an electron. And these are emitted when a nucleus undergoes beta plus decay. So positrons are also symbolized by beta plus, as we'll see when we look at some of the processes by which nuclei decay. Nuclei can undergo radioactive decay through different processes, and one of those that we'll look at is alpha decay. So in general, unstable nuclei can decay spontaneously, or in other words, without the input of energy, like in a nuclear fission reaction. And the emitted particles can fly off with high energy, and they can be harmful because they can ionize electrons, even from the human body. Now in all nuclear decays we'll look at, the nucleon number, being the number of protons and neutrons, as well as the lepton number, being the number of electrons and neutrinos and their antiparticles, being the positron and the antineutrino, as well as charge, are all conserved. Now alpha decay occurs when a nucleus ejects an alpha particle. So for example, we have a uranium-238 nucleus decaying into thorium-234. So we end up with a smaller nucleus, and an alpha particle is also ejected. So recall the alpha particle is a helium-4 nucleus with 2 protons and 2 neutrons. So if we check the conservation of nucleon number, we can see that we have 238 on the left hand side and 234 plus 4 on the right hand side. And lepton number is conserved because we don't have any electrons, neutrinos, or their antiparticles in this reaction. And charge is also conserved because we have 92 protons on the left and 90 plus 2 protons on the right. Beta decay is another type of radioactive decay that occurs in two processes. And the first one we'll look at is beta minus decay, where a neutron changes to a proton. So this occurs because the neutron to proton ratio is too large, causing the nucleus to be unstable. So here we can see one of the neutrons of carbon gets transformed to a proton for the carbon-14 nucleus to decay into the nitrogen-14 nucleus. So checking our conservation laws, being the nucleon number, we see there's 14 nucleons on the left and 14 on the right. And checking the conservation of charge, we see that we have 6 protons on the left and 7 on the right. So therefore, we must have an electron which has a nucleon number of 0, as it's an electron, and a charge of -1. So now charge is conserved. And checking the lepton number, particles have a lepton number of +1, and antiparticles have a lepton number of -1. So therefore, where we have an electron which has a lepton number of +1, we have an anti-electron-neutrino having a lepton number of -1. So this gives a total of 0, and on the left hand side we don't have free electrons or antineutrinos, so therefore the lepton number is also conserved. So given these three conservation laws, we see that when a neutron transforms to a proton, an electron is released, and so is an antineutrino, such that these three conservation laws hold. So note that this type of decay is caused by the action of the weak nuclear force. And a typical example of this type of carbon-14 decay is to date archaeological artifacts. So if you have a sample, you'd measure how much carbon and nitrogen is in it, and you'll be able to use the half-life of carbon-14 to predict how old the artifact is. Now beta plus decay is when a proton is transformed to a neutron. So this occurs when the neutron to proton ratio is small. So here we have more protons than we do neutrons. So therefore a proton is transferred to a neutron, and then checking the conservation laws, we have the nucleon number being 13 on both sides, so that's conserved. And now we have 2 little protons on the right hand side compared to the protons in a nitrogen nucleus. So therefore we must have a positron to balance that charge. And now that charge is conserved, we check the lepton number. So a positron, being an antiparticle of an electron, has a negative lepton number, and a neutrino has a positive lepton number. So recall its antiparticle had a negative lepton number. So that gives a total lepton number of 0 on the right hand side, and we don't have any leptons on the left, so the lepton number is also conserved. So therefore when a proton transforms to a neutron, a positron is released, and then an electron-neutrino is also ejected from the nucleus. So that's the difference between beta minus and beta plus decay. Gamma decay typically occurs when a nucleus has already undergone alpha or beta decay, and the excited nucleus decays to a lower energy state by emitting a photon. So here we see potassium-42 undergoing beta minus decay, where a neutron gets transformed to a proton, because there's two little protons in this case, being 19, compared to the number of neutrons, being 23. So recall the conversion from a neutron to a proton results in an electron and an antineutrino being emitted. So as we can see, now there's 20 protons in the calcium nucleus and 22 neutrons. So this nucleus is still in a high energy or excited state. So we represent this with a star, and therefore for this nucleus to jump back down to a lower energy state, a photon is emitted in the form of gamma radiation. So this here is an example of gamma decay, which does not alter the identity of the nucleus because it has the same number of protons, so therefore the same identity, being calcium. But gamma decay allows a nucleus to relax and shed energy. So essentially the nucleus emits a photon of energy to drop to its ground state. For each of the following nuclear decay equations, identify the type of radioactive decay and balance the equation using the three conservation laws. Well, for the first one, we see potassium decaying into a calcium nucleus and an additional proton on the right hand side. So therefore, in this case a neutron gets transformed to a proton, which is beta minus decay. So we see the nucleon number is balanced. So now we balance the charge. So 19 protons on the left and 20 on the right means we must have an electron on the right, which has a negative charge. And therefore to balance the lepton number on both sides, we add an electron-antineutrino to the right hand side. Now in the second reaction, we have the difference between the nucleon numbers being 4 and the difference between the protons being 2. So to balance this equation, we must add an alpha particle on the right hand side. So this is an example of alpha decay. And here we have the radioactive decay of carbon to nitrogen, where a neutron is transformed to a proton, because we have an additional proton on the right hand side. So this here is also an example of beta minus decay. So again, the nucleon number is balanced, and we add an electron to balance the charge, and an electron-antineutrino to balance the lepton number. And in the next equation, the identity of the calcium nucleus has not changed. So we see the nucleon number and charge are both conserved. So therefore this would be an example of gamma decay.